So let's start our afternoon session. And the first speaker is Du Pei from the University of Southern Denmark, who will talk about boundary condition and phases of quantum field theories. Please, welcome.
Thank you very much. It's a pleasure to be here, and thank the organizers for the invitation and the great work putting together this wonderful event. So this is going to be based on some ongoing work, rather condensed version, especially suitable for mathematicians, is going to be contained in this upcoming paper, which is a math paper trying to construct a novel type of 4D T-gravity. But then, more suitable for physicists would be this multi-part series, whose part 1 is also coming out soon. Future papers, yes, to appear. And you see, like, there is some uncertainty in when this would appear. But well, let's say that I'm certain for the time being. So the goal of this talk is to discuss something about phases, which I don't have to say are extremely useful and important because they are everywhere. They are more familiar phases, like the 3 phases of water, and more exotic ones, like superconductivity, superfluidity, confinement of quark, deconfinement of quark, so on and so forth. So typical way of detecting different phases is by using order parameters. And in fact, one important mission, maybe one of the most important for theoretical physicists, is to characterize and distinguish between different phases. And order parameters are traditionally vacuum expectation values of point operators. So maybe one of the most famous example for this is the ferromagnetic and paramagnetic transition. So if you start with a magnet, then the spins are pretty much aligned. But then you start to heat it up, then around the Curie temperature, something special happens. And after that, then the spins are not aligned and are somewhat at random. And one way to distinguish these 2 phases is to use the vacuum expectation value of some local operator. That's basically some operator that capture the average of magnetic spin, like around a neighborhood of a point. And for this phase, this order parameter is non-zero. For this is 0. And then you know, like, there should be like a phase transition between those. And throughout the past century, this has expanded a bit. For example, we know we don't need to just look at point operators. Extended objects are also useful. The most famous examples being the Wilson line and the 2 lines. And the area law of these kind of line operators can detect phases of gauge theory. So that's something many of you have learned in either undergrad or graduate courses on quantum field theory. So these are one-dimensional. Higher dimensional objects are also useful related operator known as a two-flux is a two-dimensional, and that also has some applications. And in general, there has been discussion about using surface operators to detect phases. For example, in work by Gukov and Kapustin, where they point out some interesting applications of using surface operators. So in a sense, what I'm going to talk about today is a continuation of this work, because I'm going to talk about the boundary conditions. And boundary conditions are, of course, supported on the boundary. So, let's say that this is the your space-time, and then the boundary condition are supported at the boundary, which is, of course, codimension 1. And it can be viewed as a codimension 1 extended object. But one important difference from this story to here is that we are not looking at a particular boundary condition. Like here, when we use either this operator or Wilson line to detect phases, we are thinking about a particular operator. For example, the Wilson line is inserted at some specific location and is colored by some representation. But here, the point is that we're not fixing the boundary condition. We actually use the space of all supersymmetric boundary conditions. So it is not that a given boundary condition gave you an order parameter, but instead, they collectively give you an order parameter. So there's a word, supersymmetry, that might be, I don't know, either comforting or scary to hear, depending on your background. For some of you, you may be more interested in phases of, let's say, non-supersymmetric theory. So why are we considering now supersymmetric boundary conditions? What's the justification for this? So one remark is that if we are interested in gapped phases, gapped phases means that if I look at the energy spectrum, there's a ground state, let's say like it's at energy equal to 0. And then the excited state, there's going to be a gap, literally, in the spectrum. So it costs energy to excite it. And at this is gap in the bulk. So we are not introducing boundary yet. So at low energy, we don't have access to these excited states. So one can just ignore about it and only keep the ground state. But a system with only ground state is supersymmetric in a boring way. So gapped phases basically have an emergent supersymmetry. Because, well, you just XQ on the ground state, any ground state, by 0. And that's not compatible if there are higher energy states, but are compatible if there are only ground states, because the Soucy algebra looks like some translation. And for gap phase, let's assume it has translation invariance. And now, this makes sure like all the translations, including the Hamiltonians, would just X by 0. So therefore, one can have this trivially acting supersymmetry. Therefore, one can consider now supersymmetric boundary conditions. So in fact, today, we're going to look at some phases which you might not think like previously as supersymmetric theories. So these include 2D ZK, finite group gauge theory. So one can also refer to it as Digraph-Witten theory with gauge group ZK. And in the same dimension, U1 at level K gauged WZW model. So this is a 2D theory, and it's a dimensional reduction of the more famous U1 at level K abelian transaminate theory. So transaminate theory living in 3 dimensions, you consider that on a circle. You get this as a 2D theory. Another phase that we are going to compare with those is CP K-1 supersymmetric sigma model. Of course, this theory has supersymmetry in the UV. So these are, well, you usually would not say like they are supersymmetric, but still, one can look at their supersymmetric boundary conditions. For some of you, it might appear somewhat strange to put all 3 in different columns because they are related. So for example, the work of Witten a long time ago tell you like there is a continuous path relating the CP K-1 sigma model with U1 gauge WW model. Then it has to be in the same phase, right? And there is also more or less standard claim that these 2 are also the same TQFT because they have the same spectrum of operators, and the operator has the same relations. All the algebraic data seem to be the same. So why are we putting this at different columns? So let's try to make some attempt in distinguishing them using old-fashioned method. So that's an assumption of this is a gap system. So there are no massless excitations. So for massless excitations, you can excite them slightly. And then you want that state to be also supersymmetric. So then you are forced to add superpartners for any massless particles that you have. Does that answer the question, or? No. It's the opposite. So if it's a gap, then at low energy, you forget about all the massive states. The ground state is supersymmetric in a boring way. But it's not true in the opposite direction, right? We know that there are SCFTs, conformal theory, that are also supersymmetric. Yeah, we know it's a gap. And yeah, at very low energy, yes. If one just keep the ground state, yes. But the massive spectrum will not be supersymmetric. Any more questions? Yes. Yeah, so the central charge is just zero. Central charge is just zero. So U1 level K actually have a central charge if you view it as a 3D theory. And then what that means is that yeah, now if one reduce to 2D, naively, it's not a problem relating them. But later we're actually going to see there's a remnant of that. So it depends on whether it's a, yeah, so it's a gauge. So first of all, there's a central charge of the conformal theory. So this is a gap, so there are no massive degree of freedom. So central charge of that as a conformal theory equals zero. But then there is a notion of topological central charge of the 3D theory. For that, the 3D parent of this has not shown a topological central charge. But that's a slightly different thing, and we are actually going to revisit it later. Okay, so let's try to distinguish maybe those, although it seems to be indistinguishable, but let's still try using some more traditional method. So the most boring invariant of a gap phase is the ground state degeneracy. So number of ground states. And if you view this as a supersymmetric theory, you can say like this is Witten index. But there's no difference because actually there are no fermionic ground states. So slash Witten index. And okay, so what are the number of ground states? So we are looking at ground states of a 2D theory on a circle with periodic boundary conditions. And for ZK theory, these are given by holonomies of ZK. So there are K different ground states on a circle. For even at level K, K is W model. It's a reduction of Chern-Simons theory, and Chern-Simons theory has K Wilson lines. Each can generate a state on a circle. So there's also K. So in other words, if you leave that to 3D, this is asking about the Hilbert space of the 3D theory on a torus. For U1 level K, that just counts the number of Wilson lines. For this, it turns out to be also K because the Hilbert space is the cohomology of CBK minus 1. For CBK minus 1, the cohomology is K-dimensional. So therefore, this seems to support the well-known conclusion that they are just the same. One can try to do slightly better by looking at algebra structure. Because, well, for TQFT, you not only have just this vector space, it's actually algebra, because you can do this topological evolution. So there's no usual evolution, but there's a topological evolution from two copies, one copy, that give you an algebra structure. What's the algebra for decay theory. That's just wrap decay as a ring. So in particular, you can think of it as a polynomial ring in one variable, but with a relation that x to the k equals 1. So that's the algebra of operator in the ZK theory. The U1 and level K theory, the algebra will be the same as the algebra of Wilson lines in transaminase theory. So that's a graph of U1 level K. You can think of this as either some representation of quantum group or positive energy representation of the loop group. But if you just work it out, or just work out the algebra of Wilson line in the transaminase theory, you'll find that this is equal. So it's isomorphic as a ring to this one. How about here? So the algebra, well, the cohomology is already an algebra, but famously, for supersymmetric sigma model, the algebra is not just a naive algebra given by the products in cohomology, but it's supposed to be the quantum cohomology. So if one set this 1 to 0, that's a usual cohomology. And the quantum correction is exactly about turning this 0 to 1. So again, one recover this algebra. So far, they seem to be completely identical. But now we're trying to do something slightly fancy by looking at the space of all supersymmetric boundary conditions for this, and for this. So now there are basically two types of theory. One is sigma model, another is TQFT. So we need some tool to access the space of supersymmetric boundary conditions, first for sigma models and then for TQFT. So let's when you say that it's in the infrared. Yeah, in the infrared, at the infrared phases. So of course, the sigma model have massive thing, and the ZK will not have a massive. Yeah, but we are trying to look at universality classes, right? So that's the usual thing what we do for classifying infrared physics. So let's first look at sigma model. For that, we have a claim for, so maybe number 1, for 2D supersymmetric, we only assume 1, 1 sigma model with target M. The space of supersymmetric boundary conditions, so that's supersymmetric boundary conditions is classified by the complex K theory homology of M. So this is, usually written without the U. So this is a complex K theory. And if one, so the sigma model itself has time reversal symmetry. So it makes sense to look at the space of this kind of boundary conditions with time reversal symmetry. And then you will be classified by KO homology of M. So this is somewhat reminiscent to some other results, including the relation between D-branes and K-theory. But this is just a level of sigma model, so we are not doing string theory, at least not yet. And also, very importantly, this is actually homology, not cohomology. And for general M, they are somewhat different. And then for 3D, n equals 1 sigma models, the classification is given by TMF homology of M. So this stands for topological modular form. So if you were around for Mayuko's very nice talk last week, you have already heard about it. If you haven't heard about it, just view it as some more complicated version of K-theory. So that's some remarks. Yes. Boundary. Yes. Right. So that's why there's a difference between these homology groups with TMF itself. So let me get to that in a second. So one remark is that, so here, these groups, they are abelian groups, right? For KU is basically, at the point is like Z0, Z0. But the statement can be actually upgraded into a spaces. So, and the space would, well, there's a standard operation in generalized homology theory by, well, regarding this as a homotopy group of KU smash product with M plus. M plus means M adding a point, adding a disjoint base point. And similarly for all of those guys. So the first remark is actually related to Kolya's comments or question. So these spaces are module spectrum of KU, KO, TMF as a ring spectrum. So what's the meaning of that, and why is that the case? So this can be viewed as the extension of the Stolz-Techner program. Which recover the Stolz-Techner program if you are looking at this at a point. So, so what is the physical motivation for this? So if you look at bulk theory, let's say T, you look at its space of all supersymmetric boundary conditions. Let's denote it by BT. Then this space has an action of theories, supersymmetric theories, that are well defined by themselves. So this would be a particular 2D theory. So let me write T2D. And it can be viewed as in the space of boundary conditions of the trivial theory. Trivial means that there is a single bosonic massive vacuum. And then the space of boundary conditions for that are just the theories that are well defined by themselves. So this is special choice. So let's give you a name, so curly T. Because you can stack, then this gives the structure of the space of boundary conditions, the structure of a module over the space of a theories. And the SOLTechnic program gave you some conjecture about what these spaces should be, either for 2D theory or 1D theory. And then the space of boundary condition will be module spectrum for those theories. So this might sound somewhat abstract, but let's so it depends on the bulk theory, right? So if it's a gap with a finite many massive vacuum, then you would expect that it should be finely generated. So in particular, in the cases that we are dealing with today, we are going to only see finely generated things. But it's a very good question, what actually happens if you are at a conformal point. In some cases, interestingly, it's still captured by some finely generated thing. So to give some examples to demystify module spectrum of some ring spectrum, let's look at some of these spaces more concretely. So first, Ku. So for Ku, it's 2-periodic. This is because for 1D quantum mechanics, you can have a gravitational anomaly, and that's classified by Z2. So 1D quantum mechanics can be on the boundary of the ARF theory. So if you know what I'm talking about, or alternatively, there can be a fermionic zero mode. It's 2-periodic because you have 2. You can write down a mass term getting them. So, so therefore, it has 2 graded pieces. And KUI would denote these graded pieces. For in degree 0, this is BU and Z. So BU is the classifying space for the infinite dimensional unitary group. So maybe still sounds scary, but this is some concrete space that you can concretely write down the cell structure. So it's infinite dimensional, but hopefully not too scary. Although the first space is U, the infinite dimensional unitary group. And the homotopy group of this, so I of Ku, which is the same as I0 of KUI are respectively Z and 0. This is famous about periodicity. For complex K theory, you get Z0, Z0, Z0. And similarly, there is KO. For KO, it's actually aperiodic. This is because, well, now the fermionic zero modes are Majorana fermions, and they preserve time reversal symmetry. If you want to gap them, you cannot just gap 2 of them. You have to gap 8 of them. So this is famous results from Kitaev and company. And the spaces that appear are BO times Z, O, O mod U, U mod SP, BSP times Z, SP, SP mod U, U mod O. And it's aperiodic. And the homotopy groups are just a group of components on the other side. So this gives you a Z, there are Z copies. O has 2 components. So this is Z2, Z2, 0, and then there's a Z, 0, 0, 0, and then it becomes periodic again. So you should really think these spaces as something has the action of those spaces. So you pick a point on the space of boundary condition, you pick some other points over here, and then they can produce some other boundary condition. So is this fine with everybody? So let's explain the reasoning behind this claim that I have just erased. Like why the space of boundary condition in a supersymmetric sigma model are given by KU, KO, PMF homology. So this turns out to be a generalization of Witten's celebrated work relating Morse theory and supersymmetry. So, yes.
Which one refers to which?
So 2 debulk, 1 deboundary, that's KU module. With time reversal is KO. Yeah. And then KMF is a 3 debulk, 2 deboundary. Yes. And M itself does not have to be framed. M itself does not have to be framed. So because this is a 1,1 sigma model, for 0,1 sigma model, you need a string structure, and that's if you are given a framing, that can give you a string structure. These are not exactly topological insulators. So although some classification looks similar, but this is actually classifying certain quantum mechanics with certain gravitational anomalies. More questions? So the work of Witten gave relation between ground states in a 1D sigma model. I'll just write sigma m for a sigma model with target m with cohomology or homology of the Morse Snell Witten complex. And how is that complex constructed? Well, you have 1D equals 2 sigma model with some target. And one can turn on a deformation, turn on real valued function as a superpotential. And it's convenient to just think of this as the height function. So we are assigning each point the value of its projection to this real line. And then there are critical points. And this complex is constructed by taking index I critical points. And index means the number of downward directions. So here, there's a critical point of index 0. That's a generator for C0. And for each critical point, that generates a factor in this. So that's the perturbative ground states with fermion number I. But then one needs to take into account non-perturbative effects, and these are instantons, and they correspond to Morse flows. And the analysis of Witten tell us that only the index 1 flows are useful. And they generate a differential, namely they square to 0. And so therefore, we'll have this complex. And the cohomology or homology of this complex, that's the same as the homology of the manifold. So that's Morse-Witten theory. So what shall we do now? We are now just replacing this with either 2D or 3D. And here, when now are not having just a vector space consists of ground states, but instead space of boundary conditions. So I need to replace this with basically Tj. The jth space in the space of theories. So T can be Ku, Ko, or TMF. So for TMF, this would be a Z-graded. So you not only have a complex, each of this has its own gradient. So it's no longer complex, but it turned out to be E1 page of a spectral sequence. So the differential on the E1 page are still generated by index 1 flows. So if you take cohomology of the D1 differential, now you end up with the E2 page. And then these are not freely generated by the critical points, but now it's a homology with coefficient in Tj. Oh, that's I. And this is the second page of the Atiyah-Herzberg spectral sequence. Spectral sequence. Yeah. Wait. In the case of KO, yes. Yes. Well, it's a slightly different story. So maybe you have in mind some other occurrence of a Atiyah-Herzberg spectral sequence in the study of SBT. But so here is different. Everything is going to be generated by Morse flows. And these characteristic classes also play some useful role, but they will appear much later. So here we are repeating the analysis of Witten. So we are first turning on a throw potential, and then perturbed vacua are labeled by critical points. But then there are going to be domain walls between them. And then we are trying to incorporate these domain walls. So we are basically condensing the domain wall. And the question that what happens when we condense the domain wall? And the claim is that they still correspond to differentials. But a crucial difference is that here, there are higher differentials. And they correspond to higher Morse flows, higher index Morse flows. So they are flows that relate those. For Witten, it was not important. For this generalized story, they are important. So let's just maybe give a concrete example. Target is M, right? And we are analyzing the space of boundary condition by turning on Morse function as a throw potential. So it's actually in parallel with this story. Of course, there you can ask the same question. It's not so simple to argue, but there one can prove that if you change the throw potential, this is related by chain homotopy. So here, from physics, one expects that it should not depend on this because, well, these are just deformations in physics. And as long as we keep the spectrum gapped, then it's not going to do anything interesting. So. It is important in the sense that if we have degenerate critical points, that lead to some nuance in the story, right? So we prefer to start with just for each critical point, it's just one-dimensional, a massive vacuum. And that's the easiest thing to consider. But these kind of differentials, in a sense, they are combining critical points, right? Sometimes canceling them, and sometimes combining them to something more complicated. So yeah, but certainly to get a Taylor-Huddleworth value sequence, you should start with a non-degenerate, really Morse function. Yeah, so this does not depend on the Morse function. Right. Right. So CP K minus 1. So this theory have K critical points with index 0, 2, all the way to K minus 1. And there is no 1. So because it's a CP2, CP1 is a sphere, and there are no index 1 critical points. So therefore, the usual the dimension. Yeah, yes, that's right. Yes, right. So there are no index 1 flows for this Morse function for like a generic, nice Morse function. So therefore, the homology are just freely generated by these critical points. And the same is actually true for Ku. So Ku of Cp K minus 1, that's just K copies of Ku. So it's again really generated, but for Ko, one needs to take into account some higher Morse flows. And they are higher Morse flows, for example, between those. Also between 6 and 8. These are related to the second Stiefel-Whitney class of certain submanifold. For example, CP2 is not spin, and that's related to this. Anyway, so there are some flows, and one need to deal with those. These are higher differentials there. And after the commutation, one basically, for each pair, one have a copy of Ku, but there can be something unpaired. So certainly there is something not paired at the bottom. So there are some copies Ku, but then there can be something also not paired as differential to anything. So there can be, depending on whether it's even or odd, another copy of Ko, and it's shifted by 2K minus 2. So then we know what should we put here. So, well, Ku, Ku to the K, for Ko, is that answer. We also need to understand what happens for T-clef-T. And for a nice class, known as semi-simple T-clef-Ts, the association with Ku and Ku is also fairly easy. So basically, is semi-simple, meaning that the algebra of operators can be diagonalized. So it can be put into the form EI times EJ equals to delta IJ EI. To get KU, you either just get KU for each copy or a shifted KU, depending on whether this is bosonic or fermionic. But to get KO, one needs to regard this as a P minus TQFT. So there's a time reversal. So you also want to keep the information about the action of time reversal. So it will become a KU for each pair related by time reversal, but a shifted copy of KO if this is for something that is fixed by T. And the shift is given by something that I refer to as Z8 valued Frobenius Schur indicator. So it's some interesting objects, interesting thing that you can associate to states in P minus TQFT, or actually more broadly, 3D TQFTs. Okay, so let me tell you what the results of applying this to complete the table. So if you look at KU, there are only bosonic states. So for all of those, you get just K copies of KU. So it seems that Witten is right after all. They are the same phase. And these are, people are right, and these are the same phase. But if you look at KO, actually they are different. For this, everything is unshifted. So let's take K equals to 1, 2, 3, 4. It will be KO, KO plus KO, KO plus KU, KO plus KU, plus KO. For this, it will be almost always shifted. So you see that they are only the same if K is 0 mod 4. Otherwise, they're actually different phases protected by time reversal symmetry. So on this side, similar, KO, and then KO plus KO2. KO plus KU, KO plus KU plus KO. 6. And actually, these are never the same. So is there anything wrong with this argument? Well, it turns out that we can construct a deformation, but that deformation does not respect time reversal symmetry. So the deformation that he used the complexified Fi parameter of some gauge theory. And we know that if you turn on the imaginary part, that actually breaks time reversal symmetry. So this would be the CP K-1 phase. This will be the U1 level K phase. And the deformation that Witten constructed is something like this. But if one want to have time reversal symmetry, one is restricted to this line. And what this tells us is that there's actually a second order phase transition happening somewhere here. So I'm running out of time. I just conclude by saying that these kind of invariants, they are very delicate, and they can use to detect a lot of phases. And in fact, for the semi-simple TQFTs, this invariant is a universal order parameter. Namely, they are actually also complete. So if the KO module are identical, then the two P minus TQFTs have to be related by deformation. And the same here. So in a sense, if you're only distinguishing nice gapped faces, then you only need to compute this. And there are a bunch of other interesting phenomena in 3 dimensions, but since I'm over time, let's end here.
Okay, we had plenty of questions during the talk, so let me relegate all other questions to the break, and we will start in 15 minutes with the next talk.
Thank you. Oh, the algebra of operators would not care about time reversal. So therefore, this, well, basically reproduce this if you just take the dimension. And this kind of shift, they are harder to detect, but they have to be actually compatible with the algebra in some way. So there are some way of relating them, but not directly. But if you are curious, for example, about this, there's a relative shift. This is actually related to Zohar's talk last week. This is related to the fact that if you have theta angle equal to pi, there is some anomaly going on. And that's actually the origin of this non-trivial shift. So, but you see, like, it's kind of hard to detect this. But just look at the algebra. Well, they are the same as spin TQFTs, but different as P minus TQFTs. Yeah, so if you want to preserve time reversal, there's no deformation between them, unless you go through a point with second order phase transition. So here it's just some fermion become massless, and then that can change the TQFT in some way. Yeah. Well, it's actually like a super conformal theory, right? Not only fermion become massless, the whole multiplet will become massless. The CFT, well, I don't have a good description of it, actually. So when asked about this, sometimes people tell me that there shouldn't be any because, well, Witten didn't mention any. And if you look at it, you don't find anything. But I think the problem is that because of how FI parameter got renormalized, this point is pushed to like some point very far away from the origin. So therefore, it's a bit hard to actually tune to that place. And that's another way of seeing like this kind of thing has some power. So it tells us something that we are not so sure about before. So it's not going to be at zeta equals 0. So if you lift this to 3D, it's going to be at zeta equals 0. So there's a 3D lift of the story. The two phases in 3D are also different. And then in 3D, this parameter is real. So actually, they are just different phases. But if you reduce to 2D, the affine parameter got renormalized. And it's actually pushing this point to like the infinity. Yeah. But still, there is some point. You have to pass that point to reach the other phase. Yeah, so that's a slightly different framework, right? So here, by TQFT, I mean non-extended, but these are TQFTs that are semi-simple, meaning that they have almost a trivial extension to points, except that in these cases, you have to deal with anomaly. And then there's maybe some problem in defining mathematically in the framework of, let's say, Lurie, this category. But you should view this as something compatible with the categorical picture. Namely, for each object in the category, that's generate 1 copies of KO. For 2 objects related by time reversal, that generate a KU. Well, the problem is that there's no currently framework to talk about this as an extended TQFT because of the Fermionic-Zermelo problem. It's the same as transempty theory. You don't have an existing framework to talk about the category of boundary conditions because, well, it does not have topological boundary conditions, only conformal boundary conditions. So that's hard to deal with. Well, for transempty theory, in general, there is no topological boundary condition, right? So therefore, if you want to define a category, that might be just empty because there are no topological boundary conditions. So it's similar. So I don't know how to extend this to points, but this makes sense as a non-extended TQFT. Oh, sorry. You are right.
Okay, maybe we will continue the discussion during coffee break
Maybe that's,
because we
can
need,
do this during the break.
let's thank the speaker again.